Hello, in this short video I'm going to talk you through how to use the TI-84 to do the normal probabilities for you instead of using the tables. It is very easy to access the menu, whether you've got the old OS or the new OS. Ultimately the syntax is the same. Second vars selects the distribution menu, and then from there you want the normal CDF, normal cumulative density function, and then the syntax is the lower bound, the upper bound, the mean and the standard deviation. It really is that simple. If you needed to calculate the probability that the standard normal variable z lies between -2.1 and 1.76, that's all you do. You enter those things precisely. -2.1 lower bound, upper bound 1.76, comma, mean of 0, standard deviation of 1. And straight away you get the answer 0.94293. The calculator needs both bounds, the upper bound and the lower bound. So what if there is only one bound listed? For instance, IQ follows a normal distribution with a mean of 100 and standard deviation. What's the probability that someone selected at random has an IQ greater than 143? Well, whenever we do any normal question, it's a good idea to sketch the curve so we have a much better understanding of what's actually being asked. So in this case, the mean IQ is 100. The standard deviation is 16 to the critical point, so 143 is all the way up here. And I want the area above 143. So surely, for sure, 143 is the lower bound, but the question is, what is the upper bound? Well, technically it's infinity, but do we really need to do that? As you'll note from the normal tables, the tables only go as far as 3.4 standard deviations away from the mean. Virtually nothing occurs beyond there. So we don't need to use infinity. If the standard deviation is 16 and we're based at 100, then pick a rough number using 1,000 as an upper bound. So 143 to 1,000 gives us a probability of 0.003599. Using 1,000,000 also gives us 0.003599. And if we're a little bit more conservative, 5 standard deviations is 5 times 16 is 80. So 6 standard deviations is basically what 200 is. Using 200 as an upper bound, I still have 0.003599,502. So it's still accurate to 8 decimal places, which is way more than we need. So as a rule of thumb, give yourself at least 4 standard deviations as the other limit and you should be totally fine. So if y follows a normal with a mean of 120 and a standard deviation of 38, and I wanted to find the probability that y was greater than 90, well, as always, sketch the curve. The mean is 120, so 90 is below the mean but not as far as 1 standard deviation below the mean, so it's kind of up here. And I want the probability of being bigger than that. So again, 90 is the lower limit, but what is the upper limit? Well, I said 4 or 5 standard deviations. Well, 4 times 38, well 4 times 40 is about 160. 120 and 160 is 180. So let's suppose we call this upper limit 300. And if we do that, we get the answer 0.78508. So don't worry too much about what the other limit is, as long as it's definitely far enough away. So 5 standard deviations certainly works. Finally, another distribution function that we occasionally need to use is the inverse normal. This is the thing which finds the z value or the value associated with a particular probability. The syntax is inv norm, area, mean, standard deviation. But the important thing to understand is that this returns the value where that area is to the left of it. So it definitely returns values like that. So you just have to be careful that the area you're talking about really is a left-hand area. So in this example, the random variable capital X has a normal with a mean of 345 and a standard deviation of 46. Find the value k such that the variable takes a value bigger than it with a probability 0.274. The variable takes a value bigger than it with a probability 0.274. Well, it's symmetric, so for sure the probability of being more than 345 is 50%. So if it needs to be 27%, this guy needs to be up here. So what I've done, what it's really asking, is to find this value where this area is 0.274. The problem is that is a top tail area and not a left area. So what's the left area associated with this? Well, clearly it's just 1 minus that. So 1 minus that is 0.726, so we need to use that left-hand area, and we find out that the value is 372.6, which certainly is consistent with the diagram. It's much bigger than the mean, so we're good. And finally, the hardest question on an inverse normal really is to do with this symmetric intervals. So we have a distribution with a mean of 28 and a standard deviation of 3.4. I want to find a symmetric interval, so the same side, the same distance either side, which captures 82% of the data. So on a symmetric interval, same distance either side, where 82% of the distribution lies between those two values. That's not at all what we can use with the inverse normal. However, if there's 82% inside, then there's 18% not included, and because it's symmetric, that means there's 9% in either tail. 9% below this guy and 9% above, or in other words 91% below that guy. So we want tail areas of 9% and 91%. And it does that for us straight away. 23.44 to 32.56. So there you go. I hope that all makes sense, and good luck with all your calculations. Remember, always sketch the curve so you're absolutely clear whether you're talking about a left tail area or a right tail area, a left bound or a right bound.